Dear students, now we are going to start lesson 16, which is operating reserves part 2. So this is mostly theoretical. We'll discuss the other aspects of reliability evaluation of operating reserves. Last lesson you have been introduced to the concept of outage replacement rate. You have understood that for operational phase the forced outage rate is replaced with outage replacement rate for reliability evaluation computation. Okay. Or in fact the COT comes in between, and we have seen a problem in the last class. Okay. With that basic knowledge, we now come to various other approaches for operating reserve reliability computation. So one such concept is area risk curve. What is area risk curve? Consider a single unit represented by a two-state model. The risk function is given by this equation lambda, which is e to the power minus lambda t, where lambda is the failure rate and this is an exponential distribution. The probability of a unit failing in time t. Why it is important failing in time or the lead time t? Because it is during that time the generator has committed to provide the reserve, and if it fails it will fail to provide that reserve. Therefore outage will occur only when the reserve fails to operate within the lead time, and that probability can be given by this equation, which, as you know, an integral will mean an area under this curve. Okay, so the probability of a unit failing in between the 0 to lead time is the area under the curve between 0 to t. The evaluation of the risk of a complete system for certain time into the future can be depicted using the area risk curve. So, two more question can be asked. What is an area risk curve? Okay. So, this is that area risk curve where this exponential function is plotted, and the area below it is the probability that the reserve or the operating reserve will fail during lead time. If it fails, then there will be loss of load. In that case, because the system demands it, so there will be loss of load, and this probability we are computing. Now, how to model rapid start units? Like, what are rapid start units? Like hydro and gas turbines. So rapid start units can be represented by a four-step model in which the failure rate is given by lambda ij, nij by ti, where lambda ij is the transition from state I to j, nij number of transitions from state I to j, ti is the total time spent in state I during the period of observation. The stochastic transition probability matrix in this case will be given by the current state into the number of transitions in the exponential, the probability to the power number of transitions. This P is known as stochastic or probabilistic transition probability matrix. Now this rapid state units, as we just discussed, can be modeled as four state: in service, ready for service, failed to start in the time of need, and failed. Okay, and various transition between them. Then coming to modeling hot reserve or the spinning reserve units. So what is an hot reserve? Hot reserve means the turbo alternator is shut down, but the boiler is left in the hot state. Cold reserve means the boiler is completely shut down. So hot reserves are modeled by this. Say it requires a 5-state model. Okay. So the hot reserve is either in service, or it is on reserve, it fails to take up the load when demanded, it fails, but most importantly it is not yet started, the boiler is shut down. Under what condition it is there and the transition between them. Another kind of concept which is utilized for operating reserve reliability evaluation is the postponable outages. The assumption that a unit which fails during operation must be immediately removed from service is acceptable in planning studies but not in reserve calculation. Okay. So a reserve is generally not removed from the service. Many of the failures that occur in practice can be tolerated for a certain period of time because the reserve may not be required for that time, and the removal of unit for repair can be delayed or postponed. In this case, the unit continues to supply energy and did not be removed until the load decreases to a level at which the unit is no longer needed. So in this case, we use the postponable outage model where O is known as the operating state, F is the fail state and removed from service, and P is the postponable outage state. Okay. So let lambda 1 be the rate of use outages that can be postponed, lambda 2 rate of outages that cannot be postponed, lambda 3 rate at which postponable outages are forced into failed and removed from service stage. They failed and they are removed, they are not postponable. In this case, beta is the proportion of lambda that can be postponed. Okay, and this shows the same thing in a pictorial way, and these terms O, F and P have been explained in the previous slide. Another advanced concept in operating reserve reliability evaluation is the security function model. The security function approach defines the events as breaches of security, which have been defined as inadequacies of spinning capacity, unacceptable low voltage, transmission line or equipment overload, other intolerable operating conditions. In this analysis, the evaluated security index is a global security risk index considering or comprising generator and transmission violations. However, above may not be useful for operators since it does not contain all the relevant information to perform remedial functions. So you can have a security functions which can be created like this, where PIT is the probability that the system is in state I at time t in future, QIT is the probability that the system I constitutes a breach of security at time t in future. So far we have seen unit commitment risks. Now we will have an overview of what is response risk. The techniques discussed so far enable the operator to decide which units and how many should be committed at decision time t is equal to 0 to meet the system criteria before a lead time t. However, the amount of spinning reserve is not indicated. If the dispatched unit fails, the spinning reserve must respond within certain time. Generally, two time periods are of interest: a short time span of 1 minute, a longest time span of about 5 minutes. Short response time indicates the period in which sufficient capacity must respond in order to protect system frequency and tie-line regulation, whereas the longer time indicates the need to take emergency measures such as load steering. Okay, it's important, understand this. Short for tie-line regulation and system frequency. Typically, the response rate may vary from about 30% of full capacity per minute for a hydel plant to about 1% of capacity for thermal power plant. Now, what are the factors affecting response risk? Effect of distributing spinning reserve. Okay, it reduces the risk. Effect of hydroelectric units. Since hydro units usually respond to change more rapidly than thermal units, they are useful for spinning reserve units. However, since they are cheaper to operate, they are also used as base load. Frequently, a compromise is used in which part is dispatched and remaining part is used as spinning reserve. Effect of rapid start units. As an alternative to conventional hydro units are gas turbines. Some gas turbines can reach full output within 5 minutes from standstill. If the unit responds fully, then it is only required to evaluate amount of response. Alternatively, the rapid start unit may fail to start, and this can be incorporated with various conditional probability concepts. So with this, we complete lesson 14. Lesson 16, I think, 15, 16.